Let's continue our discussion on the overall model test. We saw if the test is rejected, there is a problem in the mathematical model, either in the observations, in the functional model, or in the stochastic model. Now we will look at the line fitting problem or the sea level example and elaborate more on these three scenarios. Assume we have a time series of observations. The functional model can be written as expectation of y equals ax, and the uncertainty in the observations described by the Q matrix with uncorrelated and equally variance observations with the variance of 2 cm squared. In the first example, let's assume we have an outlier in the observation vector. Here are the results of applying the blue on this line fitting problem, where the fitted line is in the top plot and the residuals are below that. The 95% confidence interval for both the line and also the residuals are also shown. Note that for the residuals, I put the confidence interval around the expectation 0, as we know the expectation of the residuals of an unbiased estimator should be 0. The overall model test statistic is computed as 76.2 in this case. The threshold can be computed from the chi-square distribution with degree of freedom m-n, or 18 in this case. We have 20 observations and 2 unknowns of the line model, so 20 minus 2 equals 18 degrees of freedom. I chose the level of significance as 0.05 or 5%, resulting in the thresholds of 28.9. We can see that the test statistic is larger than the threshold, and so the test is rejected. A closer look at the residuals clearly indicates that we have an outlier. Let's remove the outlier and apply the estimation again. Here are the results with the new test statistic. Note that the threshold is also different since we have removed 1 observation, so the number of degrees of freedom has changed and is 17 in this case, resulting in a different threshold. Now, the test statistic is smaller than the threshold and the test is accepted. So, by removing the detected outlier, we in fact adapt the mathematical model, and now we can conclude that for the second case, the mathematical model can overall sufficiently describe the observations. Now, let's look at other scenario. Same functional model, same number of observations, same covariance matrix, but we have a set of new observations. I estimate the model and compute the residuals and the confidence interval. The overall model test is again rejected. In this case, we can see by eye that the model is not linear. In fact, the correct model is the quadratic model, which I know because I myself simulated this dataset. If I choose the quadratic model, we see that the overall model test is accepted. Note that the threshold in this case is different due to the different number of unknowns in the second model. The quadratic model has 3 unknown parameters, so the number of degrees of freedom is 17. Here, by choosing the better model, we adapt the mathematical model, resulting in the acceptance of the test. Let's look at another example. Now we have again a linear model, but with another set of observations. In this case, there is no outlier, and the functional model is also correct, and it is linear. Again, I know this because I simulated this data. Also, sometimes in practice, we deal with these kinds of problems, where we are quite almost 100% sure about both the observations and the functional model. If we estimate the model parameters for this case, it gives us these results. The test is again rejected. If we look closely to the residuals and the corresponding confidence intervals, we can see already that many of the residuals are outside the confidence interval. We can say that the interval is too narrow. Perhaps our stochastic model could not sufficiently describe the statistical properties of the involved uncertainties. To adapt the mathematical model, I should update the stochastic model. In this case, I should scale the covariance matrix properly such that the test is accepted. Now let's apply blue again, but this time with the new covariance matrix. This time, instead of using the initial assumed variance of 2 squared centimeters, I scale up the covariance matrix by a scaling factor which is computed as the ratio of the test statistic of the first model and the degree of freedom m-n, resulting in the scaling factor of 5.3. Now, multiplying the initial variance of 2 by the scaling factor of 5.3 results in bigger variance, in this case 10.6. And now we can see the results. We see that the test has been accepted. In this scenario, the stochastic model was wrong. In fact, the variance of the observations in the first case had been assumed to be too small. By adapting the stochastic model, we have solved the problem. These 3 examples demonstrated 3 different sorts of rejections of the overall model test. In these examples, it was easy to find which problem is the main source of rejection, and we easily adapted the mathematical model. It was easy because of our a priori knowledge about each case, and also the fact that in each scenario there was only a single problem with the mathematical model. In practice, however, it is not that much simple. We may have multiple outliers. We may have some outliers and also some imperfections in the functional model. In principle, any combination of these 3 discussed sources can happen. Diagnosis of the source of the rejection of the overall model test requires sometimes intuition, creativity, and a priori knowledge about the involved models and their underlying physics in reality. In fact, when the test is rejected, we can only conclude there is something wrong in the mathematical model, and as an answer to what is the source of the problem, we have multiple hypotheses. There could be observation errors, the functional model could be imperfect, there could be poorly defined stochastic model. Exact identification of which hypothesis is more likely in a systematic way is a very interesting and in-depth topic in testing theory, and is unfortunately beyond the scope of this introductory course. With this, I would like to conclude this lecture, and let's now look at some more examples and exercises.